Okay, so hello everyone. Today we're talking about the minimum spanning tree. So let's get started. So today's lecture's plan is like this. First, we will talk about what is the minimum spanning tree, and then we will talk about two algorithms that can find the minimum spanning tree. First one is Kruskal algorithm, and second one is Prim's algorithm. So, but before we need to talk about the weighted graph. So, what is a weighted graph? Weighted graph is a graph where we associate weights or costs with each edge. So as you can see here, we have the vertices like 0, 1, 2, 3, and 4. And the edge between them, they have some kind of weights. Like here, as you can see, these numbers represent the weights of each edge. And this type of the graph is called weighted graph. In real life, weighted graph can be used to represent many things, and one of them, for example, flight networks, electric circuits, and GPS navigation systems. So in all of them, the weighted graph can be used in order to represent the data. So next, what is the minimum spanning tree? Minimum spanning tree is uh, it's a subgraph of some undirected graph, and that's like subgraph, or also we call it tree, that is a both tree and spanning. Tree means that subgraph should be connected and acyclic, and at the same time it should be spanning, which means that it should include all the vertices in a graph. And the goal of the minimum spanning tree is to find a tree that is spanning and with the minimum weight in all possible cases. So, for example, here, let's say that we have here undirected weighted graph, as you can see, and let's consider which one can be represented, which can be as a candidate for the minimum spanning tree. For example, this one cannot be minimum spanning tree because, as you can see, um, the minimum spanning tree here represented with the black edges, with the black colored edges, and this one is not minimum spanning tree because, as you can see, they are not connected. And according to the definition, our graph should be connected. And this one is also not minimum spanning tree because, as you can see here, this tree, it has cycle. So actually it's not a tree because as you know, the trees, then they don't have any cycles, but this one is that it has cycle. That's why this tree cannot be minimum spanning tree. It should be acyclic, means no cycles. And this one is this is a minimum spanning tree. So in all possible variants of the spanning trees, this tree is with the minimum edges, and it covers all the vertices, as you can see. And there is no cycle, and it's connected. So it means it's connected um, from every edge, from every vertex. We can have a path to any other vertex. And the total cost of this minimum spanning tree is 50. 50 we got from the summing up all the edges that we have in this tree. So minimum spanning tree has this kind of properties, and the minimum spanning tree exists and unique if all the edges are distinct edge weights, actually, like there is no duplicate weights, and the graph is connected. In that case, if we satisfy these two conditions, then we will always get the minimum spanning tree, and that minimum spanning tree will be unique. Next, let's talk about the cut property. Cut is a partition of the vertices into two separate sets. And for example, here in this graph, as you can see, this one is undirected graph, and the uh, vertices which colored with the white, it's one set, and the vertices that is colored gray, it is a um, second set. And coursing edge is the edge that connects two separate uh, sets. For example, this edge, this edge, this edge, this edge, this edge, and these edges, they are crossing edge because they connect vertices from two different sets. And here, as you can see, among all these edges, this edge is with a minimum weight. So we have many ways to find the minimum spanning tree, and actually there are four algorithms which can find the minimum spanning tree. First one is a Kruskal algorithm, second Prim's algorithm, third one reverse delete algorithm, and fourth one is Barufka's algorithm. Actually, reverse delete algorithm is kind of reverse to this algorithm. It's kind of vice versa to the Kruskal algorithms. But today we'll talk only about Kruskal's algorithm and Prim's algorithms. By the way, all these algorithms are greedy algorithms. If you remember, we covered what is a greedy in a course of Introduction to Algorithms. But so let's take a look on a greedy. So what is a greedy? Greedy is an algorithmic strategy where on each step we'll try to make the most optimal solution with the hope that we will get global optimal solution. So here, greedy algorithm always find the local optimal solution with the hope that it will lead to the global optimal solution. So next, let's talk about the Kruskal algorithms. So what is a Kruskal algorithm? In a Kruskal algorithm, in order to find minimum spanning tree, first we need to sort the edges in ascending order. Then we add next edge to the tree unless they would create a cycle. For example, here, as you can see, this one is undirected weighted graph, and here we have the weights, and the weights are sorted according to the values that it has. And first we start with the minimum edge with a minimum value, which is the 0.7. So this one, 0.7. So we added the edge into our minimum spanning tree, and it at the same time it doesn't create any cycle. Then we have on order edge between 2 and 3, and it has value 0.17. So we added this edge into our minimum spanning tree, and if we add them, there is still no cycle. Then we add 1.7, and it has this kind of weight, and if we add it to our minimum spanning tree, it wouldn't have any cycle here. Next, 0.2, if we add them, there is no cycle, so we got this kind of minimum spanning tree. Then we add edge 5.7, and if we add them, it doesn't create still no cycle. Next, we have the edge between 1 and 3. But here is the problem. If here, as you can see, if we add 1 and 3, then we will get cycle. So that's why we don't add that edge to our minimum spanning tree, so we just skip it. Then we have again the edge between 1 and 5, and it has this kind of value, as you can see. And here, as you can see, the edge 1 and 5, if we add them, then we will create the cycle. So that's why we also skip this edge. Then we have this kind of edge. So as you can see, if we add them, there wouldn't be any cycle. There would be a cycle. That's why we don't add them. Then we add this edge between 4 and 5, and as you can see, if we add them, they wouldn't be any cycle. So then we have edge 1 and 2, but here as you can see, if we add them, then we will get the cycle. That's why we don't add that edge. Then we have 4 and 7. As you can see, 4 and 7, if we add them, we will get the cycle. So that's why we skip also this edge. Then 0 and 4. And here, as you can see, between 0 and 4, if we add them, we will get the cycle. That's why we also skip them. Then we get 6 and 2. And if, as you can see, if we add them, there wouldn't be any cycles. That's why we add this edge. Then between 3 and 6, as you can see, if we add them, then we will get a cycle. That's why we skip it. And this edge, if we add them, then we will get some cycle. So that's why we don't add that edge. And in then 6, 4, if we add them, we will get again the cycle. That's why we don't skip. And in the end, we will get this kind of final result of our minimum expanded tree. As you can see, it satisfies all the requirements of minimum expanded tree. First of all, there is no cycle, and it's connected, and it's a spanning, so it covers all the vertices in the graph. And at the same time, it's connected with the minimum possible weights of edges. So guys, here is a question for you. So press pause and think a couple of minutes, or maybe even less, and think which one is correct according to this graph. Okay, the answer we will discuss during the lecture tomorrow. So one of the main challenges of the Kruskal algorithm is to detect cycle. So like when we add edge, do we have the cycle or not? In order to detect the cycle, we can use union find. So let's say that we have some tree T, and we want to determine if we add edge VW, do we get the cycle or not? So we maintain a set for each connected component in a T, and if V and W, if they are in the same set, then adding the edge VW would create the cycle. If we add two vertices from different sets, then we'll connect the two sets containing V and W. For example, here, as you can see, this here in this image, we have one set, second, 3, and 4, and here two edges, they're on the same set. So because they belong to the same set, it means if we add edge between them, then we will create the cycle. And here example, if W would be located in different set, and if they have edge between them, then there wouldn't be any cycle, but after adding this edge into our minimum expanded tree, we will get the new merged set. So here is the time complexity of the Kruskal's algorithm. As you know, we need to get the sorted edge, and so we need to use operation sort. We need to use sort only once in the beginning, and the sorting itself takes E log of E. So E is the number of edges that we have, and the overall time complexity is E log of E. Then we need to use union when we connect like two vertices from different sets. It takes v minus 1 times because we need to connect the vertices, all the vertices, and each operation would take log of v. If you remember on the previous lecture, we covered union find, and if we would use weighted union find, we would get the most optimized time complexity. So here log v means that we use weighted union find, and the overall time complexity is v log v because we use the frequency is v minus 1 and each operation takes log v time. And find takes 2e. Is a number of edges, and find is necessary to determine what is the set of the vertex. And each operation of the find takes log v time complexity in the overall, because we use 2e times. We so remember we skip the constants, and we will get the e log v time complexity. Next, we'll talk about the Prim's algorithm. So what is the idea of the Prim's algorithm? In the Prim's algorithm, we start with the vertex 0, and we gradually grow our tree T. So, for example, we start with 0, and we consider all the edges connected to 0, and we choose the edge with the minimum value, with the minimum weight. And we repeat it until v minus 1 edges we have. So, for example, again, we have the same tree, and here we have the weights of the edges. So, what do? We start with 0, and we consider all the edges that is connected to the to 0, and from all these edges we take the minimum value. So the edge with the minimum value is between 0 and 7. It has this kind of value. So we add this edge into our minimum spanning tree. Then we have two vertices in our minimum spanning tree. It's a 7 and 0. And for the next point, we consider all the edges that is connected to the 7 and to 0. So we consider this edge, we consider this edge, this edge, this edge, this edge, this edge, and this edge. And among all these edges, we take the edge with the minimum weight, which is between 1 and 7. Between 1 and 7. So we add this edge into our minimum spanning tree. So we add this vertex into our minimum spanning tree. Then we consider all the edges that is connected to the 1, to the 7, and to 0. And from all the edges that we have, we take the edge with the minimum value, which is edge between 0 and 2. And it has value of this one. So we add this edge, and we get this. We add this vertex into our minimum spanning tree. Then we have we consider all the edges connected to the 1, to the 7, to the 0, and to the 2. Of course, we don't consider the edges between them, because if we consider the edges between two vertices that are already in our minimum spanning tree, then we will get the cycle. That's why we don't consider these vertices. So next, the minimum edge is edge between 2 and 3. So we add that edge into our minimum spanning tree, and we add 3 into our minimum spanning tree, and we will get this one. Then we consider again all the edges, and the next is this edge between 5 and 7. So we add the 5 into our minimum spanning tree, and we will get this kind of tree. Then we have we add edge between 5 and 4. We add this edge into our minimum spanning tree, and we will get this kind of minimum spanning tree. Then we have the 4 candidates for our minimum spanning tree. It's this edge, and this edge, and we will get we take the edge with the minimum value, which is the edge between 2 and 6. So this one. And we add that edge. And in the end, we got the minimum spanning tree. And as you can see, there is no cycle. All the vertices are covered, which means it's a spanning. And it's connected. There is a connection between the vertices, all the vertices. And this is the edges that we have in our minimum spanning tree. So here is the time complexity. So we, of course, we need to choose. We need to use data structure to find the minimum edge, and here we can use priority queue or min heap. So as you remember, priority queue is a data structure that allows to give the priority to some elements, and in our case, we can give the to the edges with a higher or with a minimum with less value, the higher priority, or we can use min heap where if you remember, it's min heap is one type of the binary heap where the root is the minimum value among all the values, and we can use min heap in order to keep the weight of the edges, and it allows us to always choose the edge with the minimum value. And here for the deleting min edge, so in order to choose the minimum edge, we need to take we need to repeat it e times, and each of the operation takes log e time complexity, and overall it's e log e. And the insertion also, like when we insert the minimum edge into our minimum spanning tree, we need to repeat it e time, and each operation takes log e, and the overall time complexity is e log e. So today's material can be also found in the book of Corman, Lasers and Rivest Stein on chapter 23, and on the book of algorithms, 4th edition, chapter 4.3. That's it. Thank you very much. Good luck. Bye.